The new topic is engineering alloy steels. Alloy steels have elements like nickel, chromium, tungsten, vanadium, molybdenum, titanium, etc. These elements are added to plain carbon steels to improve their properties like hardness, strength, corrosion resistivity, high temperature properties, etc. So, in effect, plain carbon steels have got poor combination of such mechanical properties. So, in order to improve or in order to enhance their performance, the certain kind of alloying elements are added. So, these are known as alloy steels. Alloy steels are of two types. If the percentage of total alloying elements added is less than 5%, these are known as low alloy steels. And if the percentage of alloying elements added exceed 5%, these are known as high alloy steels. So stainless steel, high speed steel, this will belong to the category of high alloy steel. High strength low alloy steel, which we are going to mention further, so it will belong to the category of low alloy steel. Some of these alloying elements have got more affinity towards carbon, so they easily form their respective carbides like tungsten, titanium, vanadium, molybdenum. These carbides are very hard in nature. So wherever more hardness and cutting ability is required, for example in high speed tool steel, these alloying elements will always remain present. These carbide formers are also known as ferrite stabilizers because they tend to stabilize ferrite at room temperature. While nickel and manganese type of alloying elements are known as austenite stabilizers because they tend to stabilize austenite at room temperature. HSLA, high strength low alloy steels, are microalloy steels having low carbon, low alloying elements. Percentage of total alloying elements like titanium, vanadium, aluminum will always be less than 0.5% only. But it is observed that if a small amount of these alloying elements are added to low carbon steel, then the performance of this low carbon steel or mild steel greatly gets enhanced. HSLA have high strength to weight ratio and are widely used in automotive industry. So wherever mild steel or low carbon steel cannot be used due to lack in strength and other properties, this HSLA may replace low carbon steel. Stainless steel is a kind of high alloy steel having more than 5% of total alloying elements added. They have high corrosion resistivity due to presence of chromium. Film of chromium oxide is formed at the surface of the stainless steel, which is passive and self-healing in nature. Self-healing in nature means if due to any reason this chromium oxide layer formed at the surface is broken, then immediately a fresh new passive layer of chromium oxide will be immediately formed, and thus your underlying material will remain protected against the corrosive atmosphere. So this is the main characteristic of stainless steel. So stainless steels are of three types. They have been divided into Three groups, Group A, Group B and Group C. Chromium in stainless steel is equal to total chromium minus 17 times percentage carbon. As we have already discussed, chromium is one of the alloying elements which have got more affinity towards carbon. So whenever the chromium is added to the steel in order to manufacture stainless steel in foundry, first of all, some amount of chromium will go in the formation of chromium carbide. So in the solid solution of ferrite or austenite, the remaining chromium which will remain left, it should always be near to 12.5% or 13%. Then only the complete stainless properties will be obtained in stainless steel. If the chromium content falls below this level of 12.5 or 13%, then the corrosion resistivity will be decreased. So this formula is useful to get an idea about the stainless properties of the stainless steel. Group A will have chromium in stainless steel less than 13%. Austenite at high temperature, gamma or austenite, can be hardened by multicyclic transformation. So at high temperature, austenite will be obtained in such type of steel, and when they are cooled at a moderate rate, because due to presence of high amount of chromium content, the hardenability will be more. So even by oil cooling, we can convert austenite into martensite. So finally, at the room temperature, in the microstructure, martensite will be obtained, and martensite is hard in nature. A typical chemical composition of group A or multicyclic stainless steel is 12 to 18% chromium, 0.1 to 1.2% carbon, and they will belong to the series of AISI 400. They have got very good hardness, wear resistivity. These are magnetic in nature, and apart from having more hardness and wear resistivity, they have got very good corrosion resistivity due to the presence of high amount of chromium content. So wherever good corrosion resistivity along with more hardness is needed, the multicyclic stainless steel is preferred. Applications are ball bearings, razors, surgical instruments like knives, etc. Group B will have chromium in solid solution more than 13%. Chromium is a ferrite stabilizer. So even at high temperature, the ferrite is obtained in the microstructure, because in the earlier slide we had seen that this carbide formers are also known as ferrite stabilizer. So if the chromium content is more, then instead of austenite, ferrite will be formed at high temperature, and this ferrite will remain stable right from high temperature to room temperature. So due to the presence of ferrite in the microstructure, this stainless steel cannot be hardened by quenching. It means the transformation of multisite is not possible, because in the heat treatment chapter we have already seen the transformation of multisite is only possible if the parent phase is in the form of austenite or gamma iron. So as in this case, group B case, where the chromium content is very high, due to the presence of high amount of chromium content, which is a ferrite stabilizer, right from high temperature to room temperature, 100% ferrite will be obtained in the microstructure, and ferrite cannot be transferred into martensite. That's why these steels cannot be hardened by multicyclic transformation. due to absence of austenite at any temperature. These are soft, ductile, apart from having very good corrosion resistivity. A typical chemical composition is 12 to 28% chromium, and it will have less than 0.2% carbon. Why the carbon content is so less? Because if the carbon content is more than 0.2, then as the chromium is a carbide forming element, so maximum amount of chromium will go into the carbide formation, and thus the percentage of chromium in the solid solution will be less than 13, and thus the ferrite will not remain stable at the high temperature. So wherever very good softness, ductility is required apart from very good corrosion resistivity, this ferritic stainless steel can be used. Group B is known as ferritic stainless steel, because right from high temperature up to the room temperature, 100% ferrite will remain stable in its microstructure. Vessels in chemical and food industries, restaurant pots, juice carrying pipes in sugar factory. So these are a few important applications of this group B or ferritic stainless steel. Now group C, it is known as austenitic stainless steel, because right from high temperature up to room temperature, 100% austenite will be obtained. What is the specialty of this group C steel? 24% minimum of total chromium, nickel and manganese should be there. Total percentage of chromium, nickel and manganese should be minimum 24%. Nickel and manganese are the austenite stabilizer, and chromium will play its role of corrosion resistivity to impart corrosion resistivity to the stainless steel. So chromium will be essentially present in all three types of steels, whether it is multicytic, ferritic or austenitic. But in austenitic steel, some amount of austenite stabilizer is also present. Austenite at room temperature is obtained. It is due to the presence of 8% nickel and 8% manganese. Both are the austenite stabilizer. And again, the carbon content is maximum 0.2%. So it is also soft and ductile like ferritic stainless steel. Plus, it will have very good corrosion resistivity. It will belong to the AISI 200 and 300 series. In its applications, you may write, it is used for food, chemical plants, utensils, wristwatch parts. So utensils in the market you may find, they may be made out of either ferritic stainless steel or austenitic stainless steel. Austenitic stainless steel is little what? Costlier in comparison to ferritic stainless steel. But they have got more corrosion resistivity than ferritic stainless steel. Why? Because the nickel will also add the property of corrosion resistivity. And nickel is the costliest element. So the addition of nickel increases the cost of this austenitic stainless steel. How can you make the difference between austenitic and ferritic stainless steel? Just by conducting a simple magnetic test. If the material is made out of austenitic stainless steel, it will not get attracted by magnet because the austenite is non-magnetic in nature, while ferritic stainless steel will easily get attracted by magnet. The austenitic stainless steel suffers from a problem known as sensitization. When the austenitic stainless steel is cooled slowly from the temperature range of 500 to 750 degrees centigrade, then along the grain boundaries, precipitation of chromium carbide may take place. which will reduce the chromium in the neighboring region or adjacent region, making the stainless steel susceptible to corrosion. So this is called sensitization. Why it has been given the term sensitization? Because due to the formation of chromium carbide, chromium content will fall below the critical level in the solid solution, and this will make the steel sensitive to corrosion. That's why the problem has been given the name sensitization. The solution is either you cool from this temperature range at a fast rate so that the precipitation of chromium carbide can be avoided, or you add little amount of titanium, because titanium has got more affinity towards carbon than chromium. So if any carbide forms, it will be of titanium and not of chromium carbide. So chromium content will not fall below the critical level required to have the stainless property. So this is known as stabilized grade of stainless steel. If the small amount of titanium is also present along with chromium, nickel and manganese, then it is known as stabilized grade of stainless steel, and this treatment is known as stabilization. Same kind of problem we may face during the time of welding. If you are going to weld austenitic stainless steel, then the same kind of problem you may face, where during the time of welding, wherever the temperature is up to its melting point, then there is no problem. But as we know that the heat affected zones will be present in the welded structure. So wherever the temperature is near to 500 to 750, so from that temperature, if it is cooled at a slow rate, it will generate the problem of sensitization due to the precipitation of chromium carbide. So again, you can avoid this problem during the time of welding by providing the water cooling in the region wherever the temperature will be in between 500 to 750, or you may directly use the stabilized grade of stainless steel. So why it is known as weld decay? Because due to the heat of weld, due to the temperature of weld, where in the portion where the temperature is in between 500 to 750, the decay or deterioration in the behavior or performance of the stainless steel is obtained. That's why it has been given the name weld decay. Next type of high alloy steel is tool steel. So tool steels have been classified on the basis of media. First is cold war tool steel. Cold war steel is again of three types. W type means water hardening. Here the water will be used as a media in the quenching treatment given to the tool steel. So in case of high carbon steel, we already seen in the hardening treatment given to this plain carbon steel. A typical chemical composition will be 0.6 to 1.6% carbon for high carbon steel. 0.7 to 0.9% carbon will be used for shock loading or impact conditions, while that is for shock loading tools like your hammers, anvils, punches, and if the carbon content is more than 0.9, it will be useful for making the cutting tools like your dice, hammers, chisels, drills, shear blades. These are the overall applications of high carbon steel, but here you may categorize it into two ways. The shock loading or impact loading conditions wherever required, like your hammers and anvils. So this will be kept in the category of 0.7 to 0.9% carbon, and carbon content more than 0.9 will be required for making drills, shear blades, wherever more hardness, wear resistivity and cutting ability is required. Whenever we subject these tool steels to water quenching, then they show the tendency of oxidation, decarburation and grain growth. Apart from these problems we may face during the time of quenching treatment to the tool steel, they have poor red hardness and poor strength. Poor red hardness means they will lose their cutting ability at high temperature, at more than 300 or 350 centigrade temperature. So this is the main drawback of this W type or water hardening tool steel. During the time of water quenching, we will also face another problem. It has got poor hardenability. It means very rapid quenching will be required, and higher the quenching rate required, more is the temperature difference between surface and center, and more will be the temperature difference between surface and center, more is the intensity of the internal or thermal stresses developed within the tool. And if the intensity of the thermal stresses developed during the time of rapid cooling exceeds a critical value, your tool may be broken into two or more than two pieces. So distortion and cracking are difficult to be avoided in W type or water hardening type tool steel. These drawbacks can be minimized by adding little amount of alloying elements like your chromium, tungsten, vanadium. Why these alloying elements have been selected? Because they have got more affinity towards carbon and their carbides are as well hard as the iron carbide. So if the total alloying element added is less than 5%, then it is called low alloy steel. So another category we are going to see now, it is oil hardening tool steel. It is a low alloy steel and the presence of little amount of chromium, tungsten, vanadium will improve the hardenability. It means less drastic quenching will be required to convert austenite into martensite. So instead of water quenching, oil quenching is permitted for this transformation to harden the tool steel. The application will remain almost similar to W type, but wherever we need to avoid the problem of cracking distortion and to improve the properties of tool steel, then oil hardening type of tool steel will be selected. Since the distortion is less, that's why the shrinkage is also less. It is also known as OHNS steel, oil hardened non-shrinkage tool steel. Third category is air hardening tool steel. It will also have the same alloying elements like chromium, tungsten, vanadium, but the total amount of these alloying elements will be more than 5%. So even by air cooling, you can convert austenite into martensite. So wherever more changes in the dimension of the tool are there, like your thread rolling, slitting dies, intricate die shapes, so this kind of steel is preferred over oil hardened and water hardened tool steel. So this was about the classification of tool steels, cold wall tool steel and their types.